Thank you very much, Henry. Now I'm very honored to invite the first and only speaker from the Faculty of Engineering. And this is one of our superstar, Professor Yael Hanein. So Yael is not only a professor, as you can see, she's also involved into CTO of one company and VP in another company. And she will talk about face value.
Okay, so I'll begin with apologizing. This is not my voice. I'm guessing too much excitement after a year of not meeting people and not speaking in front of people. Thank you very much for the introduction, which really echoes many of the topics that I want to convey in this presentation. In our research, we really work on this vision that was just presented about how do we actually get to monitor people throughout the day, 7 days a week, throughout the year. And we do it focusing really on the medical idea that was presented in the morning, which is the fact that at the present, the information that clinicians have about patients is based a lot on self-reporting and on clinical visits. So there's a huge gap between the information that we would like to have about our well-being, our physiology, our behavior, our sleep, and the kind of information that actually is being available. So it's not a COVID talk, not at all. We have done nothing whatsoever related to COVID. We did a lot of work in recent years, and this is where I want to start this presentation, on monitoring facial muscles. You will see that we do a lot more, but this is a topic that we worked a lot on and something that is very interesting and I think would be very interesting to show you and to express the kind of tools that we have. So if you take off your mask and you take off your skin, don't do it, you discover that you have a very, very interesting and complex muscular system which controls your facial expressions. Now, we haven't been using very much this system in the past year, but it's a system that allows us to communicate. It allows us to express emotions. It's part of the communication system. It's also part of who we are and the aesthetics behind what we represent. And clearly, it's a very, very important tool. So it's a tool that can be used for clinical purposes. It really distinguishes between healthy individuals and non-healthy individuals in psychiatric problems, in psychological problems, in neurodegenerative problems, and many, many, many more. So it's a system that is built on 43 muscles. You can see the names here, and you can practice your Latin if you wish. They're innervated by a nerve, basically two nerves that control each of them separately. And by the way, it's one of those things that really distinguish us from animals. Animals don't have such a complex system, definitely not a system that is related so closely with information. Okay, so it's a topic of huge interest. People have been studying this for generations, for decades, maybe for millennia. It starts, when in the academia, when people want to cite the first contributions go all the way to Darwin, who studied this very, very extensively, trying to make the link again between expression of emotions in men and animal and women. In the 60s and the 70s, there was a huge effort that is now dominating the world, the academic world, as far as we understand expressions. Paul Ekman, a psychologist who has ingrained the idea that we have 7 universal facial expressions. And this is a very, very debated topic with a lot of activity. So why is it debated? What is the complexity? So the complexity is that it combines many different topics, all the way from psychology and all the way to engineering. And the engineering here is a very fundamental topic, is how do you actually quantify these expressions? I mean, something that we do so naturally and intuitively, but how do you do it if you want to compare between individuals and if you want to use it as a quantifiable data? So there are two alternatives. One alternative that many of my engineering colleagues are very familiar with and experts in are in image processing. You can take the face and you can split it into specific elements, and then you can identify how each one of them is moving and shifting, but this is not direct mapping of the muscle activity. Or you can use electromyography, surface electromyography, which you can see on the right. I mean, she's smiling, but this is clearly very limited, both in resolution and in convenience, and definitely doesn't match the idea of people moving about, and we can record their well-being by, for example, monitoring their facial expressions. So what we did in the past 7 years or so was to develop a system and a data analysis approach that allows us to collect the data in a manner that is now completely compatible with ongoing monitoring. So these are soft electrodes, which are basically as soft as your skin. They're placed on the skin, and they can record electrical activity from the muscles. And this is what you see on the right. You see these spikes. This is the actual electrical activity of muscles residing just below the skin. But this is not enough, because just collecting this raw data or filter data is not enough to actually see the specific muscles. And you have to apply single processing approaches, and that allows you now to go down to single muscle resolution, which is a really, really fundamental thing in really allowing us to monitor down to single muscles and to single segments. So when we record, for example, the muscle of the eye, we can see not just the entire muscle, but we can see segments of that muscle, which again is very, very important if we want to address to provide data which is clinically relevant. So this is a work that we've done. This is a purely engineering work, solving a very straightforward problem of how to build better sensors that can record for many hours. Actually, you can go to sleep with these sensors. You can use these sensors for several days, and without any problems with the data quality. So we solved that engineering problem, but then comes the question of whether it's just something that we can use for mapping our facial expressions, or this is something a little bit more general. So what I want to convince you is that this is something which is a lot more general than just mapping muscles in the laboratory. Surface electromyography is something that you can use for any body part for a whole range of different applications. The range of applications go anywhere from rehabilitation, as I mentioned, in psychology, in neurodegenerative diseases, in gait analysis, in a whole wide range of applications. And since we've been in touch with so many people in so many different fields, we became aware of the need to take this technology and to make it available. And in that process, 2 years ago, we established a company named Xrays. And Xrays is really, the mission there is really, as we heard in the presentation this morning, is about a wearable technology that can measure and analyze biopotentials. And the point is that we can do it anywhere, anytime, basically with people in their completely natural behavior. In the process of doing that, and this is a very important thing to emphasize, is when you do want to measure and analyze daily activities, now basically take the technology out from the lab and allow people to be operating in a freely environment. now you have to be able not just to record all those different electrophysiological signals, just as you can see here, it goes all the way from EEG, which are the brain waves, EOG, which are eye movements. We can monitor the olfactory system, the ECG, of course, which is a very, very big signal, EMG signals, and other related signals. This is something we can do. But now, in order to make a complete system, a system that can take this data and deliver information to treatment or to make decisions about medical treatment or diagnostic, now we need to make the entire flow. We need the probes, we need the miniature electronics that would allow them to move freely with this technology. We need, of course, this electronics to be compatible with a tablet or a smartphone, and we need, of course, everything to be available on the cloud, including the signal processing, including very rapid process of analyzing the data. So analyzing the data months and months in the lab is irrelevant here if we really want to make this data accessible. So let me give you a few examples of the kind of specific applications that we can use and try to convey the complexity that is associated with taking the data or the raw data from the patient and bringing that data to the clinicians. So one example that we've been working for at least the past 5 years, this is a project that we run with Professor Anat Mielman from the Sourasky Medical Center. Anat is heading the lab for motor problems in neurodegenerative patients. It's a very long title, but in neurodegenerative diseases, many of us are, and you all are familiar that they have manifestations in motor problems. And motor problems are often very indicative of the diseases at later stages. And one of the problems in neurodegenerative diseases is to identify markers that precede the major effects that we see when patients already have a well-developed disease. And it turns out that one of the most important and very challenging to monitor is our sleep patterns, in particular sleep patterns with electrophysiological data. So smartwatches are, of course, a very, very important tool that can provide a lot of information. They can provide information about how we move, how much do we sleep. But when you actually start thinking about it, they don't really tell you the exact information about your sleep. They give you information about whether you move or not. So to be really able to provide electrophysiologically valid data, the exact same data that at the moment is provided only in special sleep laboratories, you need a system that would allow patients to do the recording, to do the measurement at home, but with the same quality that the clinical establishment is already familiar with. And this is what you see here. We designed a system that has 8 electrodes, so it's 4 forehead electrodes, 2 for picking up eye movements, and 2 that can monitor the muscles up here. And this system is used now in 2 pretty large clinical studies, one at the Sourasky Medical Center with subjects that have high likelihood of developing Parkinson's disease, and with healthy individuals in Asuta. And in both studies, what we're trying to do is to monitor patients both with conventional medical practices, which is PSG, and at the home environment. And that also allows us to do something very, very unique. It allows us to monitor patients day by day over extended duration. This is something which practically is impossible today because if you want to measure somebody's health pattern, sleep patterns, that person has to go to a sleep laboratory. And a sleep laboratory in a hospital is a very, very constrained and very artificial environment. And so if you're trying to develop a tool that checks how reliable or how quantify your sleep, not just in the very, very simple patterns, but really pick up the entire electrophysiological patterns, it's very, very important that this would be happening at home. And so this is a big project that we're hoping will be able to publish some of the recent results very, very soon. I think it's also important here also to mention that every new technology that you introduce or try to introduce into medical practice, you really have to confirm it against gold accepted standards. And so this is also a very big challenge in this line of activity. Another project which comes from a very different perspective, but also related to the face, is a project that we've done with the group of Professor Dino Levy. Interestingly enough, he's working on decision-making and how can we tell from facial expressions whether we're lying or telling the truth. So this is another big trend in the research community, not just in the medical community, also in the research community. People want to move and shift more towards natural environment. A lot of, I think Tom will probably talk about this vision, that a lot of what we do today in psychology research is done in very constrained artificial conditions. And when you want to understand how people interact, it's not enough to look at how you interact with a computer or a photo of a person on a computer or even a video of a person on a video. You want to see how two people interact with each other. And again, you need a technology that would allow you to monitor objectively these interactions. And so in this particular example, there were pairs of subjects, not a single subject, but two subjects sitting one in front of the other, and each one of them is monitored by a facial electrode arrays, and we could pick up the data and we can analyze whether we know whether they're telling the truth or not, because it's all monitored and controlled, but we can see how telling the truth or not telling the truth is manifested in their facial expression, again, in natural conditions. And the very last thing that I want to show you, so, you know, we very often end up targeting big problems of many people. And we had a very unique opportunity a few years ago to work with one individual, one person that had a problem that nobody could solve. You can see her here. Her name is Michal. She's a lawyer and a mother, and a person that had to go through a head surgery procedure to remove a tumor. And she ended up with paralysis in half of her face. And she had a very small problem. She wasn't suffering from cancer. She wasn't dying. She was healthy. The surgery was successful, but she couldn't blink. That was her only problem. Now, not being able to blink may sound simple, but it's devastating. She could not function. We have here, everything here is flashing light at us. She couldn't finish a single workday without headaches. It was very difficult for her to really conduct her life, and she was fighting. She continued to work, she functioned as a mother, but it was really, really, really agonizing. And she came to us with a friend, and they knew that it's possible to do what Duchenne did long, long, long ago. You can take 2 electrodes and you can zap the muscle or the nerve, and it would twitch. You know, Volta did it. You know the whole story with Galvani. Galvani didn't know what he was doing, but it's all about making these twitches. But clearly, you can't work with the technology that Galvani used, and the technology today is not very much different, as I showed you at the beginning. And so they knew it's possible. They knew that just by stimulating with a very small electric pulse, she can blink again. And so they came for us to help them with optimizing the electrodes so she can put them in the right place and regain her capacity to stimulate, to blink. And so without going into the procedure of animal testing and none of that, we were just working with her. She was testing on herself. Luckily, she's a lawyer, so it made the whole thing a lot easier from that point of view. But she started using those electrodes just a little bit over 2 years ago, and she didn't stop. Basically, every day she places these electrodes. You can see them right there. You can see the link down there to the movie. You can see her. Along with her friends, they established a company, NeuroTrigger. So NeuroTrigger is a company that is working with Xrays, our company, and they're now doing clinical studies in Solaski and additional. Now they started in Rabin Center, and this is just again the tip of the iceberg of the kind of applications that you can use. And so, thank you very much. These are the people that contributed, and of course, a lot of funding agencies. And again, thank you very much, and I sincerely apologize.